Within the grand architecture of our solar system, a world of intriguing contrasts and enduring questions orbits the planet Saturn. This is Dione, named for a titaness of Greek legend, a moon whose brilliantly reflective surface conceals a deep history of ancient scars and fascinating geological processes. It holds the distinction of being the fourth largest among a retinue of more than 200 known satellites. Its diameter measures just 1,120 kilometers, a span less than the width of the state of Texas. Yet, for all its modest dimensions, this frozen body guards secrets that continue to draw the attention of planetary scientists and astronomers. Our exploration today takes us to this remote moon, a place where sheer cliffs of ice tower over cratered landscapes, where enigmatic, pale tendrils stretch across its face, and where the subtle mechanics of orbital resonance have sculpted a truly unique world. Like a number of Saturn's moons, the story of Dione's discovery begins in the early era of telescopic astronomy. The first to observe it was the renowned Italian astronomer Giovanni Cassini, who identified it on the 21st of March, 1684. From his post at the Paris Observatory, Cassini had already located Saturn's moon Iapetus 2 years prior, and his work would later lead to the discovery of two more, Rhea and Tethys. In his initial records, Cassini referred to it simply as Saturn IV, marking its position as the fourth moon discovered in order of its distance from the planet. The name it bears today would not be assigned until 1847, when English astronomer John Herschel proposed that Saturn's moons be named for the Titans of Greek mythology. It was then that this distant world received its formal mythological title. The name carries a certain resonance. In mythology, Dione was a titaness, often cited as the daughter of Oceanus and Tethys, and in some accounts, a consort of Zeus. A few legends even name her as the mother of Aphrodite. Much like its namesake, the moon Dione would eventually be found to have its own surprising associations and relationships with other bodies in the Saturnian system, a detail we will return to. For nearly 3 centuries following its discovery, Dione was little more than a distant point of light seen through our telescopes. It remained a mysterious world, and we knew almost nothing about its nature. Even as Earth's observatories grew in power, the remote moon revealed very few of its defining characteristics. This long period of mystery came to a dramatic end with the beginning of the space age. Our first intimate view of Dione was provided by NASA's Voyager 1 spacecraft, which navigated through the Saturnian system in November of 1980. As the probe drew nearer, Dione slowly resolved from a simple speck of light into a complex world with its own distinct personality and features. The images from Voyager, while constrained by the technology of that era, unveiled a moon with a multifaceted surface. Dione's trailing hemisphere, which is the side that faces away from its orbital path, appeared to be heavily scarred by impacts. The most immense of these impact structures is Evander, a basin measuring approximately 350 kilometers across. Other notable craters include Aeneas and Dido, their names drawn from characters in Virgil's Aeneid. Yet, what was perhaps most captivating were the peculiar, bright streaks that seemed to weave across parts of its surface. These formations, which researchers at the time called wispy terrain, were unlike anything that had been observed on other worlds. However, with only a brief flyby and limited imaging technology, Voyager could only begin to spark our curiosity about this enigmatic moon. The spacecraft's instruments measured Dione's diameter at about 1,120 kilometers, confirming it as Saturn's fourth largest moon, following Titan, Rhea, and Iapetus. Voyager also established Dione's density at roughly 1.48 grams per cubic centimeter, a figure that pointed to a composition of mostly water ice, combined with a smaller rocky element, likely including a small silicate core. But this fleeting encounter ultimately left planetary scientists with far more questions than it answered. The nature of the mysterious wisps remained unknown, as did the story of Dione's surface evolution and the forces that had shaped this distant object. It would require a second spacecraft, this one bearing the name of Dione's Italian discoverer from 4 centuries earlier, to truly start unraveling these puzzles. In July of 2004, NASA's Cassini spacecraft successfully entered orbit around Saturn, initiating what would become a 13-year mission of exploration throughout the planet's system. This highly advanced probe was equipped with a suite of scientific instruments that would profoundly change our understanding of Saturn and its family of moons. During its long mission, Cassini performed several close flybys of Dione, at one point approaching to within just 99 kilometers of the moon's surface. These encounters yielded high-resolution imagery of unprecedented quality and a vast trove of scientific data about this once mysterious world. One of the mission's most important findings was the revelation of the true identity of the wispy terrain first seen by Voyager. What had looked from a distance like bright, streaky material deposited on the surface were in fact the exposed, brilliant faces of ice cliffs. These cliffs were the walls of enormous faults that sliced through Dione's frozen crust. Now known by the geological term chasmata, some of these features run for hundreds of kilometers and are several kilometers deep. The most prominent example is Palatine Chasmata, a tremendous network of fractures that stretches for more than 600 kilometers across Dione's face. Other significant fracture systems include Padua Chasmata and Carthage Fossae. In certain locations, these fractures can be seen cutting across craters and other surface features, a clear sign that they formed relatively recently in Dione's geologic timeline. The density measurements from the Cassini mission confirmed that the moon is composed primarily of water ice, but with a substantial rocky component, making up a ratio of roughly 40% rock and 60% ice by mass. This composition gives Dione a total mass of about 1.1 x 10^21 kilograms. Based on this density and mass, scientists affirmed the long-held belief that Dione likely has a differentiated interior, with a modest core of rock enveloped by a thick mantle of ice. The surface of Dione is exceptionally cold, with an average temperature of about -187 degrees Celsius. At such extreme temperatures, water ice behaves much like rock does on Earth, becoming hard and brittle enough to support the formation of solid geological structures like mountains, craters, and canyons. As noted, one half of Dione's surface is heavily pocked with craters, the lasting evidence of an ancient bombardment. But what is perhaps more telling than the craters themselves are the regions where craters are conspicuously absent. Certain areas on Dione exhibit clear signs of resurfacing, the result of geological processes that have wiped away older features to create smoother plains. These areas, found mostly on the moon's leading hemisphere, suggest that Dione has undergone periods of internal activity that have renewed parts of its surface. The story, however, continues with Dione's chasmata. This brilliant ice creates a dramatic visual against the much older surface material that surrounds it, which has been darkened over eons by radiation exposure and the steady impact of micrometeorites. The question that arises is what could have produced such enormous fractures. The prevailing hypothesis suggests they are a response to global stress patterns that developed within Dione's icy crust. Over billions of years, as Dione cooled and its interior structure changed, its crust would have undergone immense tension and compression, forces that eventually caused it to crack. Some researchers propose that these fractures could be evidence of a subsurface ocean that existed long ago and subsequently froze. Water famously expands as it turns to ice, so the growth of a solidifying ocean would have exerted incredible stress on the outer shell, potentially cracking it into the patterns observed today. An alternative explanation points to tidal flexing, where the constant stretching and squeezing of Dione from Saturn's powerful gravity might have generated sufficient heat and stress to form these features. The complete answer, however, still eludes us. Dione travels in its orbit around Saturn at an average distance of about 377,400 kilometers, taking 2.7 Earth days to complete a single revolution. It is also tidally locked to its parent planet, which means the same hemisphere perpetually faces Saturn. Much like our own moon presents only one side to Earth. As with many moons in the Saturnian system, Dione is part of a complex gravitational dance of orbital resonances, which has had a profound influence on its development. The most notable of these relationships is arguably the 2-to-1 mean motion resonance Dione shares with its neighbour, Enceladus. This precise relationship means that for every single orbit Dione completes, Enceladus circles Saturn exactly twice. This is not a mere celestial coincidence, but a stable gravitational lock that binds the two moons in a synchronized rhythm, affecting the evolution of both worlds. This resonance generates powerful tidal forces that produce heat inside each moon. The consequences of this heating are far more spectacular on Enceladus, which displays incredible geological activity, including the famous geysers at its south pole that continuously spray water ice into space. Dione, being the larger of the two, experiences proportionally less tidal heating from this interaction. An intriguing detail is that Dione also hosts its own small companion satellites. Two tiny moons, named Helenae and Polydeuces, share Dione's orbit around Saturn. These moons are situated in what are known as Lagrange points, which are gravitationally stable locations that lead and trail Dione on its path. Sometimes referred to as Trojan moons, these tiny companions are only a few kilometers in diameter and were likely captured or formed from debris within Dione's orbital path. The possibility of a subsurface ocean on Dione remains a particularly fascinating subject. Scientists are captivated by any location in the solar system that might harbor a liquid ocean, as these are considered potential environments for the emergence of life. The existence of such an ocean on Dione would therefore be a discovery of major significance, and there is some evidence to support the idea. Data from Cassini's magnetometer instrument revealed a weak interaction between Dione and Saturn's magnetosphere. Some scientists have interpreted this as a sign of a conductive layer beneath the surface, which could be a salty, liquid ocean. The vast fracture systems on Dione's surface also point to considerable geological activity in its history, which may have been fueled by the presence of liquid water below. Furthermore, models of Dione's internal heat budget, which account for radioactive decay in its rocky core and tidal heating from the resonance with Enceladus, indicate that it might have generated enough warmth over its lifetime to sustain a liquid layer between its core and the icy crust. If Dione does indeed possess a subsurface ocean, it would be added to a growing roster of ocean worlds within our solar system. This list includes places like Europa, Enceladus, and perhaps Titan, all of which could potentially offer habitable environments for simple life forms. Yet, unlike Enceladus with its dramatic plumes of water vapor erupting into the void, Dione displays no current signs of geological activity that would offer a direct window to any hidden ocean. If an ocean truly exists within Dione, it is concealed deep beneath many kilometers of solid ice. Since the Cassini mission concluded in 2017, when the probe was intentionally sent into Saturn's atmosphere, no other spacecraft has journeyed to the Saturnian system. This means our present understanding of Dione is based entirely on the information gathered during the limited flybys conducted by Cassini and the Voyager probes. Despite this, the scientific community has put forward several concepts for future missions to Saturn that could involve a more detailed exploration of Dione. These proposals include orbiters designed to study multiple moons, landers that could touch down on Dione's surface, and even highly specialized missions to search for direct evidence of a subsurface ocean. One especially ambitious concept is the Enceladus orbiter, which, while focusing primarily on Enceladus, could also perform numerous flybys of Dione. Another proposal, titled Journey to Enceladus and Titan, would similarly concentrate on those two moons, but would also make observations of Saturn's other major satellites, including Dione. While none of these mission concepts have yet been approved for development, the profound scientific questions raised by our brief exploration of Dione ensure it remains a high-priority target for future investigation. As we pull back from this detailed look at Dione, we are left with the portrait of a world defined by fascinating contrasts. It is a moon whose seemingly quiet, frozen surface tells a story of a dynamic and powerful past. The sprawling networks of bright fractures that crisscross its terrain speak of immense forces that have shaped and reshaped this world over its long history. The remarkable difference between its heavily cratered trailing hemisphere and its smoother leading face hints at ongoing processes that continue to sculpt its features, and subtle clues in its gravitational and magnetic fields whisper of the potential for a concealed ocean far beneath its icy exterior. In many respects, Dione exemplifies the unexpected complexity that has been discovered throughout Saturn's family of moons. What once appeared as simple points of light through our telescopes have been revealed to be distinct worlds, each with its own unique geological personality and evolutionary path. These findings challenge us to reconsider what drives geological activity in the outer solar system, where the sun's warmth is too faint to power the kinds of processes we see on Earth. Within the vast and intricate symphony of Saturn's moons, Dione plays its own unique melody, one that continues to captivate our curiosity and inspire us to look ever deeper into the mysteries of our solar system. It is, as it happens, entirely possible for a world to disappear. In the nascent era of astronomical observation, Saturn's moon Iapetus presented a profound puzzle, seeming to vanish from the sky on a regular basis. One night it would be a visible point of light, and on another it would be gone, like a masterful sleight of hand performed on a cosmic scale. Yet, as the mechanics of this trick were unraveled, the true mysteries of Iapetus only began to deepen. This is because Iapetus is a world defined by its stark dualities. One of its hemispheres is enveloped in an almost complete darkness, while the other shines with the intense brightness of reflective ice. An even more perplexing feature is the colossal mountain range that encircles its midsection, a rocky belt wrapped with uncanny precision around the equator, whose origin continues to elude a clear explanation. One must wonder why this moon possesses such a dramatic, two-faced appearance. What tremendous cataclysm, or slow, unstoppable process, could have formed a mountain chain far taller than Mount Everest in such an enigmatic location? And what clues might this distant body hold about the chaotic early history of our own solar system? The story of our understanding begins with the sharp vision of Giovanni Domenico Cassini. From the Paris Observatory in 1671, using the era's refracting telescopes, Cassini identified a new celestial object circling the great ringed planet. This newfound moon, however, exhibited a peculiar behavior. As it moved along the western portion of its orbit around Saturn, it remained fairly conspicuous, but when its path took it to the eastern side, it would appear to fade away, growing incredibly dim and often disappearing from sight completely in the instruments of the time. Reflecting on this strange pattern, Cassini noted that on some occasions, after the moon had started to fade in a 32-feet telescope, a search for it the next day with a more powerful 45T instrument would prove entirely fruitless. From these observations, Cassini drew a remarkable conclusion. The moon must have one hemisphere that is substantially darker than the other. He also deduced that it must be tidally locked with Saturn, forever presenting the same side to its parent planet, much like Earth's own moon. This tidal lock meant that as Iapetus circled Saturn, it would alternately show its bright and dark faces to observers on Earth. When its luminous side was oriented toward us during the western part of its orbit, it was visible. Conversely, when its dark hemisphere faced our direction on the eastern side, it would vanish from view. For the 17th century, this was an extraordinary insight, representing the very first time a surface characteristic had been detected on any moon beyond our own. Cassini initially named the 4 moons he found Sidera Lodoicea, or the Stars of Louis, to honor King Louis XIV, but these designations did not endure. It was later that John Herschel proposed adopting names from the Titans, the mythological siblings of Saturn. Iapetus, known as the father of Atlas and Prometheus, and therefore the progenitor of humanity in the myths, became the name for this strange world. For many centuries that followed, Iapetus remained little more than a distant speck of light, known only for its bizarre fluctuations in brightness. Even the Voyager probes, which fundamentally changed our view of the outer solar system in the late 1970 seconds and early 1980 seconds, were only able to conduct distant flybys. Voyager 1 sent back images that confirmed Cassini's deduction about the extreme difference in brightness, but the resolution was insufficient to capture any fine detail. Voyager 2 had a slightly better encounter, passing closer and providing the first tantalizing hint of another of the moon's incredible features, a suggestion of a massive ridge lying near its equator. But a complete portrait of the breathtaking strangeness of Iapetus would have to wait for the arrival of a mission dedicated to exploring the Saturnian system. That mission was the Cassini spacecraft, named appropriately for the moon's discoverer. Reaching Saturn in 2004, the Cassini probe would go on to spend 13 years revealing the secrets of the gas giant and its eclectic family of moons, with Iapetus being a high-priority target. Cassini's data, especially from a close flyby in September 2007, that brought the spacecraft to within just 1,000 640 kilometers of the surface transformed Iapetus from a remote flicker into a complex and tangible world. We now know that Iapetus is a world of low density, only 1.22 times that of water, which suggests its composition is predominantly water ice, perhaps as much as 75%. Its form is not a perfect sphere, a shape distorted in part by the Equatorial Ridge, which gives it a distinct, oblate appearance reminiscent of a walnut. It is unlikely to harbour a subsurface ocean like Enceladus or Europa, as there are no signs of recent geologic activity or the tidal heating required to keep water liquid far beneath its icy crust. Its surface is ancient and frigid, heavily marked with craters, especially in the bright expanses of Roncevaux Terra, which serve as a record of billions of years of cosmic bombardment. The Moon's orbit is also quite unusual. Iapetus travels much farther from Saturn than the other major moons, at an average distance of about 3.5 million kilometers, which is more than double the distance to the next large moon, Titan. This vast orbit results in a very long year, taking 79. 3 Earth days to complete a single revolution. Critically, its orbital path is also inclined, tilted by approximately 15 degrees with respect to Saturn's equatorial plane, where most of the planet's other large moons reside. This remoteness means Iapetus is less influenced by Saturn's magnetosphere and the powerful radiation belts found closer in. Furthermore, its orbital tilt may be a significant clue about its formation or early migratory path, possibly suggesting it did not coalesce from the same equatorial disk as Saturn's inner, regular moons. But what truly makes Iapetus so visually arresting is its surface, which is cleanly partitioned into 2 vastly different regions. Its leading hemisphere, the side that faces forward in its orbit, is extraordinarily dark. This area, known as Cassini regio, accounts for about 40% of the Moon's surface. Its albedo, a measure of reflectivity, is exceptionally low, between 0.03 and 0.05, making it as dark as asphalt or coal dust, and causing it to absorb nearly all sunlight that strikes it. In stark opposition, the trailing hemisphere, the side facing away from the direction of travel, along with the polar regions, is intensely bright. This area, which includes Roncevaux Terra to the north and Saragossa Terra to the south, has a high albedo of 0.5 to 0.6, as brilliant as freshly fallen snow or pure water ice. This nearly tenfold difference in brightness represents the greatest known interhemispheric albedo contrast in the entire solar system. To see this world up close would be to witness one side of deep, reddish-brown or black, and the other a dazzling white. In certain places, especially near the equator, the boundary between these 2 halves can appear remarkably distinct, almost as if it were painted onto the surface. In certain other regions, particularly as one moves toward the higher latitudes, the boundary becomes more diffuse. Here, bright impact craters punctuate the dark landscape, while dark material creates delicate streaks across the bright terrain, an effect resembling soil scattered upon fresh snow. A striking image from the Cassini spacecraft captures this stark division with exceptional clarity. Iapetus is a world with 2 profoundly different faces. The question of what created this dramatic hemispheric coloration has been a long-standing puzzle. For many years, the prevailing hypothesis pointed to a source from within the Moon itself. The idea was that some form of dark, cryovolcanic substance might have erupted from the interior of Iapetus, blanketing one entire side. A 1,981 paper analysing Voyager data, authored by Bradford Smith and his colleagues, made a case for this very theory, identifying a ring-like structure as a crater that had been partially filled with this dark, eruptive matter. Yet, subsequent observations from Cassini's radar and imaging systems painted a very different picture. This later data showed that the dark material is actually a surprisingly thin layer, in most areas measuring only tens of centimeters to perhaps a meter deep. Furthermore, impact craters inside the dark region known as Cassini regio frequently dig up bright, icy material from just below the surface, punching through this dark coating. This was compelling evidence that the dark substance was not rising up from the Moon's interior, but was instead settling down from an external source. A 1,982 paper, based on spectrophotometric observations of the dark, leading surface, determined that the material's composition was carbonaceous. Its signature was similar to that of the Murchison C2 meteorite, which arrived on Earth as part of a meteor shower in 1969. To account for this discovery, the authors considered potential sources near Iapetus within the Saturnian system. The most likely candidate was identified as dust, originating from Saturn's outer, irregular moon, Phoebe. Phoebe is a sizable, dark moon that was captured by Saturn's gravity, and it circles the planet in a retrograde, or opposite, direction at a considerable distance. Across billions of years, cosmic impacts on Phoebe and other small, dark moons in similar retrograde orbits have ejected a vast, though extremely tenuous, ring of dark dust particles. Solar radiation applies a gentle pressure on these tiny particles, a process known as the Poynting-Robertson effect. The consequence of this effect is that the dust slowly spirals inward towards Saturn, all while maintaining its retrograde motion. Now, let us return to Iapetus. It travels around Saturn in a prograde direction, which is the same direction as Saturn's own rotation and that of most of its other moons. However, its orbit is situated much farther out than the main rings and the inner satellites. As Iapetus journeys around Saturn, its forward-facing, or leading, hemisphere continuously intercepts this incoming stream of dark, retrograde particles that comes primarily from the Phoebe group. The effect is analogous to how a vehicle accumulates debris on its front surface while moving forward. The trailing hemisphere, by contrast, is shielded by the bulk of the moon and consequently gathers far less of this dark material. However, this deposition of dust by itself does not completely account for the sheer intensity of the darkness on the leading side of Iapetus, nor for the sharpness of the boundary between the dark and bright regions. This is where the processes of thermal segregation and water ice sublimation become critical. The dark matter that settles on the leading hemisphere absorbs a greater amount of sunlight than the bright ice surrounding it. This absorption causes the surface temperature to increase slightly. While Iapetus is an exceptionally cold world, even a minor rise in temperature is sufficient to cause the volatile water ice to sublimate, transforming directly from a solid into a water vapor gas. This process of sublimation is particularly effective because Iapetus rotates very slowly. A single day on the moon lasts for about 79 Earth days, a period that perfectly matches its orbit around Saturn. With such long periods of daylight, temperatures rise and the ice has ample time to sublimate away from the warmer, darkened areas. In fact, the rate of sublimation on Iapetus is so pronounced that if its surface were composed of pure ice, we would expect to see more than 100 meters of ice lost over the course of 1 billion years. This rate is faster than that of any other Saturnian satellite. The question then becomes, where does this sublimated ice go? It tends to recondense and freeze onto the coldest surfaces it can find. These surfaces are the already bright, icy regions on the trailing hemisphere and near the poles, which reflect more sunlight and thus remain cooler. Scientists propose that because Iapetus has a negligible atmosphere, the sublimating molecules travel along ballistic trajectories, making impressive leaps to the trailing hemisphere much like a projectile. This sets in motion a self-reinforcing cycle, often called a runaway positive feedback loop. Dark areas become slightly warmer, which causes them to lose their ice. This makes them even darker, as the underlying dust becomes more concentrated. As they darken, they absorb more heat and sublimate even more ice. Simultaneously, the bright areas remain cold and collect this migrating frost, which makes them even brighter. Their increased brightness allows them to reflect more sunlight, causing them to stay even colder and accumulate still more frost. Over millions and billions of years, this powerful process has drastically sharpened the demarcation between the dark leading hemisphere and the bright trailing one, resulting in the extreme contrast we observe today. So, the great dichotomy of Iapetus appears to be the result of two interconnected phenomena: external contamination from retrograde moons and an internal sorting mechanism powered by sunlight and ice sublimation. It is a truly remarkable example of planetary processes in action, but the two-toned coloration is only one aspect of the strangeness of Iapetus. As Voyager 2 first suggested, and Cassini later confirmed in breathtaking detail, Iapetus has another feature that is unique in the known solar system: a colossal equatorial ridge. This ridge is essentially a massive wall of mountains that extends for approximately 1,600 kilometers, covering at least half the Moon's circumference. On average, its base is about 200 kilometers wide, and it achieves staggering heights of up to 20 kilometers above the surrounding plains. This is significantly taller than Mount Everest. The most perplexing aspect of this feature is that it follows the equator almost perfectly. It is primarily located within the dark Cassini Regio, though some equatorial mountains seen by Voyager on the trailing hemisphere might be a continuation of the same structure. In images like one captured by Cassini during a close flyby, the sheer scale of the ridge is astonishing. It imparts a distinctive, compressed appearance to the Moon. What could possibly have created this immense belt of mountains? This remains one of the greatest ongoing mysteries of Iapetus. Several hypotheses have been put forth, and each has its own set of strengths and weaknesses. One of the leading ideas proposes that the ridge is a relic from a time when the Moon spun much more rapidly. Recent models suggest that early in its history, not long after its formation, Iapetus might have been rotating at a much faster rate, perhaps completing one turn in about 16 hours. This rapid spin would have increased its oblateness, causing the Moon's equatorial regions to bulge outward due to centrifugal force. This would have happened while the Moon was still young and its structure was relatively plastic or even partially molten. As Iapetus eventually cooled and solidified, this equatorial bulge became frozen in place. Over the course of millions of years, gravitational forces from Saturn gradually decelerated the Moon's spin until it achieved a tidal lock, completing just one rotation for every 79-day orbit. As Iapetus slowed, the centrifugal force that had sustained a primordial bulge began to wane, but its now solidified crust could not entirely settle back into a perfect sphere. Instead, this material slumped downwards, piling up near the Moon's midsection to create the colossal equatorial ridge we observe today. This theory corresponds well with the ridge's location and its ancient, heavily cratered surface, which strongly suggests it formed very early in the Moon's existence. A key challenge, however, is that this scenario requires Iapetus to have once rotated at an exceptionally high velocity, perhaps near the threshold of its own structural failure, and to have become solid while still maintaining that distorted shape. An alternative and equally intriguing hypothesis suggests the ridge is the result of material that descended upon Iapetus from an outside source, such as the collapse of a ring system or a small sub-satellite that once circled the Moon. If Iapetus did possess a debris ring in its distant past, potentially formed from a captured object or a major impact, the material would have naturally settled into orbit above its equator. Should that ring have become unstable, or if the orbit of Iapetus itself shifted, the ring particles might have been nudged across the Roche limit, the boundary at which a larger body's tidal forces overpower the self-gravity of a smaller one. This event could have triggered a slow, steady cascade of material onto the surface of Iapetus, where it would have accumulated primarily along the equatorial line. This model could potentially account for why the ridge appears most pronounced on the dark, leading hemisphere, if the ring particles themselves were dark, or if their deposition occurred concurrently with the influx of dark dust from Phoebe. Some simulations even indicate that a single small moonlet disintegrating within the Roche limit of Iapetus could have supplied sufficient material for the ridge. While this explanation elegantly addresses the ridge's location, the precise mechanisms for how such a ring would first form and then later collapse remain a subject of scientific discussion. Other ideas, including tectonic processes or convective upwelling from the Moon's interior, have difficulty explaining why such activity would be so narrowly restricted to the equator across such an immense distance. A singular giant impact is also considered an unlikely source for such a long, linear, and perfectly equatorial structure. Detailed imagery from the Cassini spacecraft confirms the ridge's ancient origins through its heavy cratering and shows that it is structurally composed of icy, crustal material, with some sections displaying evidence of landslides and other collapse features. Whatever the formation process was, it must have taken place very early in the history of Iapetus, likely within the first few 100 million years of the solar system's emergence. The ridge stands today as a monumental artifact of the Moon's dynamic past, a frozen record of cosmic events we are still working to fully comprehend. The Cassini mission provided a revolutionary new perspective on this captivating Moon, fundamentally reshaping our understanding. Its close flyby delivered the crucial data that cemented the theory of exogenic dust and sublimation as the cause for the Moon's two-toned appearance. It also provided remarkably detailed views of the Equatorial Ridge, enabling close analysis of its structure, even as its origin continues to be debated. With unprecedented accuracy, Cassini measured the shape, gravity field, and surface composition of Iapetus, without which the Moon would likely have remained the faint, enigmatic point of light it had been for centuries, and yet, a great many mysteries persist. What is the true origin of the ridge on Iapetus? What is the dark material on its mysterious face actually made of, beyond being something generally carbonaceous? Without returning to this world, it will be challenging to find definitive answers, and no future missions are currently planned to sample or even orbit this perplexing place. For now, we are left to ponder its dark side, a fitting state for a world that once perfected the art of disappearing. Circling the magnificent ringed giant Saturn is a world of ice and profound mystery named Rhea, the second largest of the planet's moons. While its sibling Titan often captures the spotlight, Rhea is a fascinating world in its own right, a place holding numerous secrets and wonders, from towering ice cliffs to an internal structure that challenges scientific models. It is time for this less celebrated moon to emerge from the shadow of its giant neighbour. Rhea was first observed on the 23rd of December 1672 by Giovanni Domenico Cassini, the Italian astronomer whose work was foundational to our knowledge of Saturn and its moons. Named for the Titan goddess from Greek mythology, this moon has captivated scientists for centuries. As Saturn's second largest moon after the colossal Titan, Rhea has a diameter of 1,528 kilometers, making it approximately half the size of Earth's moon. If placed on our world, it would stretch the distance from London to Warsaw. It orbits Saturn at a distance of about 527,000 kilometers, completing a single revolution every 4.5 Earth days. Like many large moons, it is tidally locked in a synchronous rotation, ensuring the same hemisphere perpetually faces the planet. Rhea's surface is among the most reflective in our solar system, with an albedo of 0.7, meaning it reflects 70% of the sunlight it receives. This gives it a brilliant white appearance against the blackness of space, a direct result of its composition, which is primarily water ice. But this does not make it a uniform, featureless sphere. On the contrary, the moon is heavily cratered, bearing the scars of ancient impacts that tell a story of a long and violent history. The largest of these impact basins, named Mamaldi, is an impressive 480 kilometers across, a distance comparable to that between Paris and Amsterdam. These craters are more than just blemishes. They serve as windows into the moon's past and its internal makeup. Observations have revealed that the floors of some craters appear darker than the surrounding landscape, a detail suggesting that impacts have excavated material from beneath Rhea's bright, icy shell, possibly exposing darker, amorphous water ice and melted material from the force of the collision. A view of Rhea's southern hemisphere reveals a crater surrounded by bright, excavated material, but what truly stands out is the moon's network of luminous, wispy streaks that crisscross its frozen landscape. These features were first noted in images from the Voyager space probes during the early 1980 seconds, yet their fundamental nature remained a mystery for decades until the Cassini mission provided much clearer pictures. Originally believed to be deposits of ice or frost, these wisps were eventually identified as immense ice cliffs, with some rising hundreds of meters into the sky. Their formation is thought to be a consequence of tectonic forces in Rhea's distant past, which caused the icy crust to fracture and push certain sections upward. These formations offer valuable insights into the moon's geological past and the forces that have sculpted its surface across billions of years. However, the enigmas of Rhea are not confined to its surface. In 2010, analysis of data from the Cassini spacecraft prompted a surprising revelation. It appeared that Rhea possessed a tenuous atmosphere, or an exosphere. While a minimal amount of gas surrounding Rhea is to be expected, the discovery of a measurable quantity was not anticipated. This atmosphere was found to be composed mainly of oxygen and carbon dioxide, with the oxygen component being approximately 5 trillion times less dense than the atmosphere of Earth at sea level. Despite being incredibly thin, the simple existence of this atmospheric layer posed fascinating questions regarding its source and persistence. One hypothesis proposes that the oxygen is generated when ions from Saturn's magnetosphere strike water ice on Rhea's surface, causing it to decompose. The carbon dioxide, conversely, is believed to originate from the oxidation of organic molecules on the surface by the exosphere's oxygen. This finding distinguished Rhea as the first moon with a known oxygen atmosphere beyond Jupiter's moons Ganymede and Europa. It also created new opportunities for studying the intricate dynamics between Saturn's moons and the planet's formidable magnetosphere. While Rhea's exterior is captivating, its interior holds its own secrets. Although we cannot directly see beneath Rhea's icy shell, scientists have employed various techniques to infer its internal makeup. Based on Rhea's mean density of 1.236 grams per cubic cm, which is only modestly greater than water, it can be deduced that the moon is predominantly water ice, accounting for about 75% of its mass, with the remaining 25% being a smaller portion of rock. This composition has led to Rhea often being characterized as a frozen, dirty snowball. Such a structure places Rhea in sharp contrast with bodies like Earth's moon, which are primarily rocky. During its visit, Cassini's instruments also returned crucial information about Rhea's composition. Spectroscopic data not only confirmed water ice as the main surface component, but also identified traces of other substances. A notable finding was the detection of carbon dioxide trapped within the surface ice. This suggests that Rhea's ice is not pure, but instead contains other compounds, which, due to its higher moment of inertia, might even include complex organic molecules. The prevailing scientific view is that Rhea is not differentiated into distinct layers. It is instead considered to be a largely homogeneous mixture from surface to center, with the possible exception of its core. This model has been challenged, however. In 2006, a paper published in the journal Icarus put forward the idea that Rhea could harbor a layer of liquid water beneath its surface, constituting a subsurface ocean. This concept remains highly speculative and lacks the strong supporting evidence seen for similar oceans on moons like Europa or Enceladus, yet it presents an alluring possibility for future missions to explore. The confirmation of such an ocean would carry profound implications for Rhea's potential to host life, and for understanding the conditions that allow for liquid water in the outer solar system. Another of Rhea's puzzles is its shape. Whereas many large celestial bodies are pulled into a nearly perfect sphere by their own gravity, Rhea is distinctly non-spherical. It exhibits a slight flattening at its poles and a bulge around its equator, a form known as a triaxial ellipsoid. The curious aspect is that Rhea's shape does not align with what would be expected from its current rate of rotation. This inconsistency has prompted scientists to suggest that Rhea may have a non-uniform internal structure, with denser materials concentrated away from its core. One of the most significant chapters in Rhea's recent exploration involved the Cassini mission's close approaches. A collaborative effort between NASA, ESA, and the Italian Space Agency, the Cassini probe dedicated more than 10 years to exploring the Saturn system, which included several intimate encounters with Rhea. The nearest of these flybys took place on the 11th of January 2011, when Cassini passed just 76 kilometers above Rhea's surface. Its final close pass occurred on the 9th of March 2013, at an altitude of 997 kilometers. These approaches enabled the spacecraft to capture extraordinarily detailed images of the moon's cratered topography and collect important data on its composition, ultimately determining that Rhea does not possess an internal magnetic field. These flybys have given us our most detailed view of Rhea's surface features to date. The images revealed a landscape defined by two main terrain types: heavily cratered regions and younger, smoother plains, first hinted at in earlier Voyager imagery. The heavily cratered areas are believed to be ancient, possibly originating from the solar system's formative era. These old surfaces act as a chronicle of the period of intense bombardment that defined the solar system's youth. The smoother plains, by contrast, are likely the outcome of a resurfacing event, perhaps caused by material thrown out from major impacts. This ejecta would have settled back onto the surface, infilling older craters and forging flatter expanses. Yet perhaps one of the most compelling findings from the Cassini mission was something it failed to find. Before Cassini's arrival, some scientists had theorized that Rhea might possess a ring system. This hypothesis stemmed from unusual measurements of electron densities near Rhea, recorded by Cassini in 2005. Nevertheless, despite targeted searches during its flybys, Cassini discovered no proof of rings orbiting the Moon. While this non-detection does not entirely exclude the possibility of some form of debris disk, it does make it considerably less probable. Another fascinating quality of Rhea is its position within Saturn's intricate family of moons. Rhea travels in its orbit through Saturn's vast E-ring, a diffuse halo of ice particles believed to originate from the cryovolcanic plumes of Enceladus. While Rhea itself shows no signs of the geological activity seen on its sibling moon, its location within this ring ensures a constant interaction with these icy grains. Although Rhea resides in the outer, less dense reaches of the E-ring, this prolonged exposure over eons could influence its surface characteristics and account for the Moon's notably bright appearance. Reflecting on our current understanding of Rhea, it becomes apparent that this world, often eclipsed by its more prominent neighbours, is an object of deep fascination. From its ancient, heavily cratered hemisphere to its contrasting, smoother side, and from its incredibly thin atmosphere to its role in Saturn's intricate family of moons, Rhea continues to capture the curiosity of scientists and inspire our collective imagination. Yet our exploration of this moon is far from complete, as a great many questions persist. The precise nature of its internal structure remains unknown. We have yet to fully understand how it has changed over the billions of years following its formation. A key question is whether it could potentially harbour primitive life within a hypothetical ocean beneath its surface. These inquiries and others await future voyages to the Saturnian system. Though no missions are currently planned with Rhea as a primary target, the Moon will almost certainly be studied by any subsequent spacecraft dispatched to investigate Saturn and its satellites. As we conclude this part of our journey, it is worth appreciating the sheer diversity of worlds within our own solar system. From the searing heat of Venus's surface to the frozen plains of Pluto, and from the colossal volcanoes of Mars to the potential subsurface seas of icy moons like Enceladus, our cosmic neighbourhood is rich with wonders yet to be explored. Rhea, with its frozen surface reflecting the faint light of a distant sun, serves as a quiet monument to the profound beauty and mystery of the universe. As our quest for knowledge continues, one can only wonder what secrets this remote moon might one day share. While Tethys may be an unfamiliar name to many, it is a world defined by its resilience. This icy satellite, orbiting Saturn at a distance of 295,000 kilometers, might seem unassuming at first glance. That initial impression fades, however, upon learning what it has withstood, leaving a sense of astonishment that it exists at all. A closer examination of its scarred exterior reveals the story of its past. Few moons possess a colossal system of trenches that extends around 3/4 of their circumference, a tectonic fracture so immense it challenges belief for a world of its size. Directly opposite this feature, a gigantic impact basin looks back, providing clear evidence of a collision so powerful that it should have shattered the moon into countless pieces. The questions of what caused this and how Saturn's fifth largest moon managed to survive such a cataclysm are central to its story. The answers appear to be held within its frozen, icy shell, and today they are slowly being uncovered. Alex McColgan of Astrum presents Tethys as a scarred survivor, and we can delve into its history and geology. The first recorded observation of Tethys was made by Giovanni Domenico Cassini. After he began his work at the Paris Observatory, Cassini, for whom a famous probe would be named centuries later, identified Tethys in 1684 at the same time as Dione. These two discoveries were added to his growing list of Saturnian moons, which already included Rhea and Iapetus. Following the custom of the era, they were first given the name Siderea Lodoicea, or the Stars of Louis, in honour of King Louis XIV. This royal dedication, however, did not endure. Later, in the 19th century, John Herschel put forward a new naming system that drew from the Greek Titans, creating a thematic link to Saturn, also known as Cronus, the king of the Titans. Tethys, in a fitting choice for a world made of water ice, received its name from a Titaness and sea goddess. The moon is indeed exceptionally icy. A crucial characteristic uncovered by gravitational measurements mostly from the Cassini spacecraft, is the remarkably low density of Tethys, which is approximately 0.97 grams per cubic centimeter, or just 0.97 times the density of liquid water. Because of this, the mass of Tethys is less than 1% of our own moon's, even though its diameter is a third as large. This extremely low value is a strong indicator that Tethys is composed almost entirely of water ice, with only a very small fraction of rocky material mixed in. This suggests that Tethys probably never fully separated into a distinct rocky core and an icy mantle, or if such a separation did occur, the resulting core is exceptionally small. Its density might also point to a certain degree of internal porosity, which means the ice inside may not be perfectly solid and could contain empty spaces or less dense ice formations. This composition establishes Tethys as a quintessential example of an ice world from the outer solar system. In its physical appearance, Tethys is a characteristically bright, icy satellite. Its high bond albedo, which reflects about 60% of the sunlight that strikes it, confirms a surface dominated by water ice. This surface is relatively clean and lacks the significant dark, rocky, or carbonaceous materials seen on moons such as Iapetus or Phoebe. Tethys does not have a perfectly spherical shape. The gravitational pull of its neighbors has distorted it into a triaxial ellipsoid, meaning it has 3 different axes. Still, perhaps the most striking visual on Tethys is one of its major landmarks, Ithaca Chasma. This enormous canyon system is the dominant feature of the moon's topography. It stretches for up to 2,000 kilometers in length, reaches 100 kilometers in width, and plunges to depths of 5 kilometers. The sheer scale of this feature is difficult to fully comprehend. To appreciate its magnitude on a terrestrial scale, one could envision a fissure stretching from New York City nearly to Denver, Colorado. In proportion to its world, it dwarfs Earth's Grand Canyon and is among the largest canyon systems in the entire solar system, rivaled perhaps only by Valles Marineris on Mars. The presence of such a monumental feature on a seemingly simple icy moon raises an obvious question about its origin. While several theories have been put forth, the prevailing hypothesis links Ithaca Chasma to the internal evolution of Tethys. This idea suggests that the canyon may have formed very early in the moon's geologic history. As Tethys came together and subsequently began to cool, any liquid water held in its interior would have started to freeze. Water, unlike most other substances, actually expands as it freezes. If Tethys once harbored a significant subsurface ocean, or even a partially liquid interior, the slow solidification of this internal water would have expanded the moon's total volume, much like an inflating balloon. This internal expansion would have exerted tremendous stress on the rigid, frozen outer crust. According to one prominent theory, Ithaca Chasma is the physical manifestation of the moon's crust cracking open due to relentless internal pressure. It stands as a global-scale fissure, a sign that Tethys froze solid from its core outward. The sheer magnitude of the chasm suggests that Tethys may have expanded its circumference by roughly 5% during this freezing process. It's a remarkable concept to consider an entire moon swelling until its surface literally began to rupture. Other hypotheses have explored potential connections to the colossal impact crater Odysseus, proposing that its shockwaves could have fractured the opposite side of the moon. However, current thinking holds that Ithaca Chasma is older than the Odysseus Basin, and detailed simulations indicate the expansion freezing model aligns more closely with the observed geology. Ithaca Chasma is therefore more than just a breathtaking feature. It is a preserved record of the thermal history of Tethys. It serves as a dramatic testament that this now frozen world might have once experienced cosmic-scale growing pains. The surface temperatures on Tethys are exceptionally low, averaging around -187 degrees Celsius. This extreme cold ensures that water ice remains brittle and stable against sublimation over all but the longest geological timescales. In this environment, the water ice on Tethys often behaves much like solid rock. Tethys is also without any discernible atmosphere, which leaves its surface completely exposed to the unforgiving conditions of space, including micrometeoroid impacts, solar radiation, and charged particles within Saturn's magnetosphere. Yet not all of these impacts were from micrometeoroids. One was so large that it came perilously close to shattering the frozen moon, like a projectile fired through a delicate globe of snow. This brings us to the Odysseus Crater. Where Ithaca Chasma tells a story of internal forces, the Odysseus Crater testifies to a history of external violence. Situated on the leading hemisphere of Tethys, Odysseus is the Moon's most expansive impact basin, measuring about 450 kilometers from rim to rim. This diameter is equivalent to more than 2/5 of the diameter of Tethys itself. The cataclysmic impact responsible for this enormous feature is thought to have happened between 400 million and 1 billion years ago. Given the crater's size relative to the Moon, there is a strong possibility that Tethys would have been broken into pieces if it had been as hard and icy as it is today. It seems, however, that the impact occurred when the interior of Tethys was still partially molten or slushy. This state allowed the Moon to absorb and distribute the impact's energy more effectively than a completely solid, brittle body could have. Interestingly, Odysseus is surprisingly shallow for its vast diameter. It lacks the sharp, bowl-like shape of craters seen on rocky worlds like our own Moon or Mercury. Instead, Odysseus is relatively flat, with a subdued rim and a central peak complex that has largely collapsed. This is not how it would have appeared just after the impact. Its current state suggests a phenomenon known as viscous relaxation was at work over geological time. Even solid ice can behave like an extremely thick fluid, particularly where there is significant topography. The immense depression left by the impact and its uplifted rim would have slowly sagged and slumped under the Moon's own gravity, gradually softening the crater's profile. The degree of relaxation visible in Odysseus offers additional clues about the thermal state and composition of the crust of Tethys, both at the time of the impact and in the eons that followed. Such a large impact would have released a tremendous amount of energy, making it logical that not everything in the vicinity would have remained frozen. The event likely resurfaced a substantial portion of the surrounding landscape, either by obliterating older craters or by blanketing them with ejected material. So, Tethys has endured significant events over its history, originating both from within and from without, but that is not the entirety of this ice moon story. Another significant discovery on Tethys involved its unusual thermophysical properties, which led to an amusing connection with a 1980 seconds computer game character. In 2015, Cassini's composite infrared spectrometer conducted a series of observations of the Moon's daytime anti-Saturn hemisphere over a 9-hour period. The resulting data confirmed an anomaly first noted in 2012. The lower latitudes of the leading hemisphere of Tethys appear cooler during the day and warmer at night compared to their surroundings. This same area on Tethys also registered as darker in infrared and UV color ratio maps than the rest of the leading hemisphere. Amusingly, the pattern, when mapped, made the Moon resemble a giant Pac-Man, a detail that provided scientists with a moment of levity and led them to name the phenomenon accordingly. Still, the Pac-Man thermal map on Tethys, and a similar one found on its neighbor Mimas, demanded a scientific explanation. Tethys orbits Saturn at a distance of approximately 295,000 kilometers, which makes it the 5th largest moon in the Saturnian system. Its orbital period is brief, just under 1.9 Earth days. And like most of Saturn's major moons, it is tidally locked. This gravitational arrangement is important because it ensures Tethys always shows the same face to Saturn, dividing its surface into a leading hemisphere, which faces the direction of orbit, and a trailing hemisphere. This orbital lock helps keep the Pac-Man feature facing the same direction, which also relates to the Moon's coloration. The leading hemisphere appears to be between 10 to 15% brighter than the trailing hemisphere, and its near-infrared spectrum suggests it has a greater concentration of pure water ice on its surface. This pattern is generally understood to be the result of external factors. The leading hemisphere is the side most exposed to weathering by particles from Saturn's E-ring and the plumes of Enceladus. This process effectively sandblasts material onto the surface, which consists of submicron-sized icy particles. Smaller particles of water ice reflect more light than larger ones, thus giving the leading hemisphere a higher albedo. The trailing hemisphere, by contrast, is more intensely bombarded by energetic plasma particles trapped within Saturn's magnetosphere. This high-energy radiation can sputter surface molecules, break chemical bonds, and implant ions processes, collectively known as space weathering, which tend to darken and redden icy surfaces over time. Contamination from micrometeoroids carrying darker materials could also contribute. In other words, we now think that Saturn's rings are responsible for feeding Pac-Man, as the differential bombardment from E-ring particles modifies the surface across the Moon's leading hemisphere. This variation in thermal inertia allows certain areas to store and release heat with greater efficiency than the surrounding terrain, which in turn produces the temperature differences that have been observed. It is a fascinating discovery, one that underscores just how deeply these moons are molded by their distinct interactions with the rings of Saturn. Tethys may not possess the atmospheric intricacy of Titan or the conspicuous modern-day activity seen on Enceladus, yet it is far from being a dull, static world. It is a celestial body that has been profoundly shaped by momentous events. Its history is etched across its face in the grand forms of Ithaca, Chasma, and the Odysseus Crater. The Moon also serves as a remarkable case study of how worlds are influenced by their greater cosmic neighborhoods. While Tethys is an icy body, the subtle shifts in its surface texture and coloration suggest there are ongoing exchanges with the Saturnian environment. Orbiting Saturn and its rings alters Tethys, and by observing both, we can gain a clearer understanding of these dynamic processes. Unfortunately, no new missions to Tethys are currently in development, but this is a moon that has endured far worse circumstances. It has been compressed by immense forces, scoured by a constant barrage of icy dust, and struck from above with impacts that could have torn it apart. Tethys is a survivor, and though its crust is composed of ice instead of rock, it is undeniably resilient. It has withstood everything the cosmos has thrown at it thus far, and continues on its journey. We now turn our focus to the most requested subject of exploration, Saturn's largest moon, Titan. The intense curiosity surrounding this world is certainly understandable. It stands alone as the only moon in our solar system with a dense atmosphere. There is also unambiguous evidence for stable bodies of liquid on its surface. Best of all, humanity has made a visit, providing a wealth of authentic photographs and video from its alien landscape. Titan is a truly remarkable, planet-like world. It is the sixth spherical moon orbiting Saturn, and in the Saturnian system, it is in a class of its own when it comes to size. Unlike the four large Galilean moons of Jupiter, all of Saturn's other moons are quite small by comparison. To provide some sense of its scale, Titan's diameter is 50% greater than that of Earth's moon, and it is 80% more massive. This makes it the second largest moon in the entire solar system, surpassed only by Jupiter's Ganymede. It is true that Titan appears slightly larger than Ganymede if they were placed side by side, but this is an illusion created by its thick atmosphere, which extends its apparent diameter. Even so, Titan's true physical diameter is still larger than Mercury, the smallest planet, though it holds only 40% of Mercury's mass. Because its density is quite low for an object of its volume, its surface gravity is relatively weak at just 0.14 grams, or 1.35 meters per second squared, which is even less than our own moon. Given its low density, the composition of Titan is thought to be roughly half water ice and half rocky material. Unlike many other celestial bodies of this size, Titan is believed to have a differentiated interior, meaning it is organized into distinct layers. Similar to many other large moons, one of these layers is hypothesized to be a liquid ocean made of water and ammonia, located beneath the moon's crust. This subterranean ocean is analogous to Earth's magma layer, which is situated between the core and the crust, and its liquid state is maintained by heat, pressure, and to some extent, tidal forces. The likelihood of this liquid layer's existence was strengthened when the Cassini spacecraft, while orbiting Saturn, detected extremely low-frequency radio waves within Titan's atmosphere. The surface of Titan is not known to be a good reflector of such radio waves, but a liquid interior would be. Further evidence comes from the observation that surface features on the Moon have shifted by as much as 30 kilometers since Cassini began its survey. This could indicate that the crust is not fixed to the core, but is instead floating upon this liquid ocean layer. And while no evidence of life has been found on Titan, some scientists speculate that the conditions within this subsurface ocean could be suitable for life to exist. If there is indeed life on or below the surface, we will have to wait some time to find out, as there are no missions planned to investigate this possibility. For the foreseeable future, Jupiter's moon Europa remains a more probable candidate for such an investigation. The differentiated interior of Titan does not generate a magnetic field. Nevertheless, the moon is well shielded from the solar wind, as it spends 95% of its orbit around Saturn inside the planet's own powerful magnetosphere. Titan completes one orbit of Saturn every 15 days and 22 hours, and its path has a fairly high orbital eccentricity, meaning it is not perfectly circular. Its orbital plane is also tilted at an angle. This does not, however, mean that Titan is likely a captured object. Instead, much like Jupiter's Galilean moons, it is thought that Saturn once had several large moons in its past. Most of these were likely destroyed in massive collisions, which left Titan as the sole survivor. Saturn's medium-sized moons, such as Iapetus and Rhea, are believed to be the remnants of that chaotic early history. Titan's day is identical in length to its orbital period, just like our own moons. This means Titan's rotation is tidally locked to Saturn, causing it to present only one face toward the planet. Visually, this makes little difference from afar, as Titan's hazy atmosphere completely obscures any view of the surface. From the surface of Titan, however, one might just be able to see Saturn, though the view would be greatly diminished by the haze. This tidal lock also means that if you were to stand in one place on Titan, Saturn would remain fixed in the sky. If the haze were removed, the view would be spectacular. This brings us to the characteristic that truly distinguishes Titan from every other moon in the solar system: its substantial atmosphere. The sight of Titan's atmosphere is often striking, as it extends so far out into space. A picture of Earth shows an atmosphere that appears to hug the planet quite closely. Titan, by contrast, looks as if it is wrapped in a thick, expansive blanket. There are several reasons for this. The first is that while Titan is significantly smaller than Earth, its atmosphere is 1.9 times more massive than our planet's, which translates to being 7.3 times more massive on a per-surface area basis. A second key reason for this atmospheric expanse is Titan's gravity, which is substantially weaker than Earth's, and thus exerts a much gentler hold on its gaseous envelope. The sheer mass of this atmosphere, however, creates a surface pressure of 1.45 atmospheres, a remarkable 45% greater than what we experience on our own planet. A direct comparison reveals just how far Titan's atmosphere truly extends into the vacuum of space. The 600-kilometer altitude marks only the upper boundary of its mesosphere, whereas Earth's mesosphere concludes at just 120 kilometers. Even at a distance of 975 kilometers, the Cassini spacecraft was forced to make orbital corrections to counteract atmospheric drag during its closest passes. Much like Venus, Titan is what is known as a superrotator, a world whose atmosphere spins faster than the body of the planet itself. This phenomenon is especially pronounced at the moon's poles. Here, each pole hosts a massive vortex that completes a full rotation every 9 hours, a stark contrast to the moon's leisurely 16-day rotational period. These polar vortices behave much like permanent, continent-sized hurricanes. The question then becomes, what is this vast atmosphere made of, and what gives it that distinctive orange color? The atmosphere is composed of 98.4% nitrogen, with the balance consisting mostly of methane and trace amounts of hydrogen. There are also minute quantities of various hydrocarbons, which are formed when ultraviolet light from the sun breaks down methane molecules in the upper atmosphere. It is believed that these very hydrocarbons are responsible for lending Titan its signature orange hue. This continuous process of methane decomposition should have depleted the moon's entire supply within 50 million years, an exceptionally brief period in the context of the solar system's age. This implies the existence of a source that is actively replenishing the atmospheric methane. The most probable explanation involves cryovolcanoes, though the possibility of a biological origin has not been entirely dismissed. The methane present in the atmosphere generates a greenhouse effect, without which Titan's surface would be considerably colder. In a fascinating paradox, however, the thick haze also reflects a great deal of sunlight back into space, creating an anti-greenhouse effect that counteracts some of the warming potential of the methane. While Titan's upper atmosphere already receives only 1% of the sunlight that Earth does because of its great distance from the sun, This additional reflection means that its surface ultimately receives just 0.1% of that light. The Huygens mission team described the challenge of photographing the surface as being similar to capturing images of an asphalt parking lot at dusk. The combination of all these factors means that while the surface would be dim, a human explorer would only need an oxygen supply and extremely warm clothing to stand comfortably on Titan. The cold there is truly profound, averaging negative 180 degrees Celsius. At this temperature, any water on Titan is frozen solid, never melting, evaporating, or sublimating. This raises a question about the clouds that are sometimes observed. They are not composed of water ice, but rather of methane. Consequently, it can indeed rain liquid methane on Titan. The moon's temperature is, in fact, perfectly situated for methane to exist in a liquid state. Methane's freezing point is negative 182.5 degrees Celsius, and its boiling point is negative 161.5 degrees Celsius. This specific combination of temperature and surface pressure led scientists to the exciting prospect of finding hydrocarbon lakes or even seas on Titan's surface, analogous to the water-based lakes and seas of Earth. If such bodies of liquid truly existed, it would be the first time they had ever been observed anywhere beyond our own world. This possibility was one of the primary motivations for the Cassini-Huygens mission to finally see what lay hidden beneath that dense, opaque atmosphere. The Huygens probe, named for the astronomer who discovered Titan in 1655, was engineered to descend through the atmosphere and touch down on the surface. Its design even accounted for the potential of landing in a liquid ocean. As the probe made its descent, its parachute deployed, and after a journey of nearly 3 hours, it came to rest on solid ground. While it did not find any active lakes at its landing site, its observations confirmed that they had once been present. Huygens had settled in what looked like a dried-up lake bed. The images it sent back showed rounded stones, very much like the pebbles found in a river or along a lakeshore on Earth. From its orbital vantage point, the Cassini spacecraft was able to confirm that liquid methane lakes still exist on Titan today. Near the South Pole, Cassini identified an area that was later confirmed to be a lake and named Ontario Lacus. It is about 20% smaller than its North American namesake, Lake Ontario, but still quite large at 15,000 square kilometers. On one side of this lake, a smooth shoreline can be seen, clearly eroded by wave action. On its western edge, the first evidence of a river and delta system on Titan was found, indicating that liquid hydrocarbons flow from higher elevations into the lake, depositing sediment in a process identical to what occurs on Earth. Ontario Lacus is remarkably shallow, with an estimated depth of only 40 centimeters to 3 meters, and its deepest point is thought to be just over 7 meters. When Cassini's radar mapped this lake, it discovered that any waves on its surface were no more than 3 millimeters high, meaning the liquid would have appeared as smooth as a sheet of glass. This doesn't necessarily mean larger waves are impossible, unless the liquid is unusually viscous. The more likely scenario is that the observations were simply made on a day with no wind. Given Titan's atmospheric density and gravity, waves there should theoretically be larger than on Earth. As the moon's north pole began to emerge from a 15-year winter, another lake, Jingpo Lacus, was discovered. During one of its flybys, Cassini captured sunlight glinting off the surface of Jingpo Lacus, reflecting like a mirror directly into the spacecraft's instruments. Further study of this area revealed more evidence of moving liquid on Titan, with visible river channels flowing into the lake. The second largest lake discovered on Titan is Ligeia Mare. Located in the northern polar region, it is larger than Lake Superior on Earth, covering a surface area of 126,000 square kilometers. While some parts of this sea are relatively shallow, its average depth is much greater than that of Ontario Lacus, at around 50 meters, and some areas could plunge to depths of over 200 meters. Numerous rivers can be seen feeding into the sea, and large islands are dotted throughout this region. One of Cassini's most puzzling observations was a feature in this sea, nicknamed the Magic Island, which seemed to appear and then vanish over time. Scientists are not certain what caused this phenomenon, but theories suggest it could have been suspended silt, bubbles rising from the depths, or even subsurface ice floating to the surface as the sea warmed during the arrival of Titan's spring. It remains a captivating mystery. Titan's largest lake, Kraken Mare, spans an immense 400,000 square kilometers. A defining characteristic of this sea is its division into two major basins, which are linked by a narrow passage that brings to mind Earth's Strait of Gibraltar. This channel has been aptly nicknamed the Throat of the Kraken. It is thought that tidal forces, acting across the lake's vast expanse, produce a tidal change of approximately 1 meter. Consequently, this strait might experience powerful currents and perhaps even whirlpools. When compared to Ontario Lacus, Kraken Mare is significantly deeper, although its maximum depth does not exceed 170 meters. Beyond the lakes, Titan's surface presents a host of other compelling geological features. The Moon's surface is remarkably young, estimated to be as recent as 100 million years old, which strongly implies ongoing geological activity. Some scientific models propose that the crust of dirty ice is substantially rigid. There is, however, some evidence suggesting the presence of tectonic activity on the Moon, possibly driven by the powerful tidal interactions with Saturn. The primary mechanism for surface renewal, though, is likely the very same process that replenishes methane in the atmosphere: cryovolcanism. This concept offers a fascinating contrast to Earth's geology. On our world, magma is intensely hot and solidifies upon emerging from the ground. Titan features an analogous process, but its magma is a mixture of water and ammonia. When this material erupts from cryovolcanoes and flows across the landscape, it too freezes, creating a fresh surface. Because a water-ammonia solution is far less viscous than silicate lava, it travels much greater distances. This results in volcanic mountains that are flatter and never attain the steep elevations of their counterparts on Earth. While the thick atmosphere makes definitive confirmation of specific cryovolcanoes challenging, the most probable candidate is Sotra, located in the southern hemisphere. In a processed image where the height is exaggerated tenfold, the shape of the dome and its 1.7 kilometer deep pit become clear. This is the largest such feature known on Titan. The force required for this cryovolcano to erupt must have been truly extraordinary. Although it does not appear to be currently active, it remains under active observation. The fact that Titan's lava is a blend of water and other minerals suggests that the surface can be likened to dirty ice. The way the Huygens probe bounced and settled upon landing provides a rough understanding of the surface's consistency. Scientists have described the texture as being similar to soft, damp sand. An alternative theory compares it to snow covered by a thin, brittle crust. This conjures an image of walking on frozen snow, where careful steps allow one to stay on the solid surface, but a hard stomp would cause one to sink deeply. Titan's surface is believed to behave in a similar manner. The Moon's highest peaks are found in ridge belts, formations that resemble the Rocky Mountains in America. These ridges could themselves be another form of cryovolcanic feature. Titan's tallest mountain, reaching an altitude of 3,337 meters, is located within one of these ranges, which is known as Mithrim Montes. An intriguing detail is that mountains of this height are thought to be capped with methane snow. The surface is also etched with numerous gorges and valleys, and infrared cameras peering through the haze from orbit have revealed extensive dune fields. Another prominent feature visible from space are vast stretches of dark terrain. These dark patches were initially believed to be seas, an idea that was revised when the Huygens probe landed in one such area called Shangri-La. While they may have held liquid in the distant past, they are now understood to be plains covered in dark mineral deposits. In some locations, these deposits form windswept dunes, much like those found in the Namib Desert on Earth. In many respects, Titan offers a compelling parallel to our own planet. Scientists speculate that Titan may exhibit conditions reminiscent of an early, though much colder, Earth. It is an undeniably remarkable world, and one can only hope that it will be the focus of a dedicated mission in the future. The Cassini spacecraft performed brilliantly, but it was never a dedicated Titan orbiter, and its operational life has concluded. Exploring more of the Moon's surface would be an exceptionally fascinating endeavor, and hopefully, a mission to achieve that will soon receive approval. 3 years have passed since the Cassini mission concluded with a deliberate plunge into Saturn's atmosphere. Its 13 years in orbit around the ringed planet were tremendously successful, marking it as one of the great exploratory missions of all time. The vast repository of data it gathered is still being analysed today, as many mysteries about Saturn and its moons persist. One of Cassini's most stunning discoveries was the confirmation of stable liquid methane lakes on Titan, the solar system's most unusual moon. Yet, knowing the lakes exist did not explain their origin. Now, however, scientists may be closer to an answer. Across the entire solar system, only two bodies are known to have stable liquids on their surfaces: Earth and Titan. This shared characteristic, however, does not imply they are similar worlds. Earth is a rocky planet with an iron core and a silicate mantle, whereas Titan is an icy world. Its crust and mantle are composed primarily of water ice, which encases a subsurface ocean of liquid water surrounding a rocky core. This compositional difference makes Earth much denser, and combined with its greater size, results in significantly stronger gravity. Both worlds possess dense atmospheres, but their gravitational differences have a profound effect. Earth's atmosphere is held tightly to the planet, while Titan's, though slightly more massive overall, extends for hundreds of kilometers above the surface. Their thermal environments are also vastly different. Being much closer to the Sun, Earth is warm enough to support an active water cycle. On Titan, water is frozen solid. The Moon's frigid temperature is, however, perfect for liquid methane to exist on its surface. This means Titan experiences a methane cycle that mirrors Earth's water cycle in function. Methane clouds have been observed in Titan's atmosphere, and these clouds release rain of liquid methane onto the Moon's cold surface. This precipitation carves rivers through the icy terrain, which then flow into smaller seas and lakes. Radar data from Cassini, visualized in orbital images, clearly shows a variety of riverbeds and valleys sculpted by flowing methane. The most prominent of these channel systems are found around Ligea Mare, Titan's second largest lake. The channels known as Vid Flumina are particularly noteworthy, as they appear to be significantly older than any other such feature on the Moon. These canyons possess walls that rise hundreds of meters, and they are defined by exceptionally steep slopes. While liquid methane is present within these canyons, it is not currently flowing. Instead, the features are thought to be drowned river valleys, a result of the high liquid level in Ligea Mare. It is possible, however, that some tributaries at higher elevations are still actively feeding into the main canyon system. The lakes on Titan can achieve immense proportions. The biggest of these, Kraken Mare, covers an area of roughly 400,000 square kilometers, making it larger than Earth's Caspian Sea. Radar information indicates that a great number of these lakes are quite shallow, with some being only a few meters deep. In contrast, some of the more substantial lakes can reach depths exceeding 200 meters. Taken together, this means the total volume of potential fossil fuels on Titan is more than 300 times the confirmed reserves on our own planet. A surprising quality of Titan's lakes is their profound stillness. On some, ripples are no larger than about 1 millimeter, giving the surface an appearance like glass or a perfect mirror. This observation was unexpected for scientists. They had predicted waves up to a meter high, driven by the dense atmosphere and low gravity. Several explanations have been considered for this calm, including the possibility that Cassini simply passed over when there was no wind. Other theories suggest the liquids are far more viscous than anticipated, or that the surfaces sometimes freeze over. Yet another hypothesis proposes that dense aerosols settle on the liquid, forming a film that suppresses the formation of waves. The discovery of these lakes would not have been possible without Cassini's radar instrument and infrared camera, which could penetrate Titan's dense haze. These tools relied on a method known as specular reflection to gather data. The radar first identified large, dark areas on the surface. These were later confirmed to be lakes, when the infrared camera captured sunlight reflecting off the liquid and into its lens. The effect is similar to what is sometimes seen when viewing Earth from space. This technique of using specular reflection with the sun and the infrared camera became a common method for verifying what the radar was observing. Interestingly, the spacecraft also detected clouds and the evidence of their rainfall. In one image, a light-colored patch signifies dry terrain. A year later, however, the same region was imaged again. This time, it revealed darker patches that indicated an extremely flat surface, almost certainly a collection of shallow, small lakes. The lakes are not spread uniformly across the Moon's surface. Instead, the majority are concentrated near the poles. The Huygens probe, a component of the Cassini mission that landed near Titan's equator, did observe flow channels in that equatorial region as well. This raises the question of where the corresponding equatorial lakes are. The answer is believed to lie in seasonal variations, much like how summer and winter create different weather patterns on Earth. At specific times during Titan's long year, rain would fall in these equatorial areas and collect on the surface. These pools likely evaporate during other parts of the year as the precipitation patterns shift toward the north and south, which is the state Cassini and Huygens would have witnessed. Even with its 13-year mission orbiting Saturn, Cassini was present for less than half of a single Saturnian year. It takes Saturn a full 30 Earth years to complete one orbit around the Sun, meaning Cassini could not have captured a complete picture of all seasonal changes. It is highly probable that the lakes change in depth throughout the year, and some may even disappear entirely for a time. Cassini's data presented another mystery concerning Titan's lakes, one that may have only recently been solved. Some of the Moon's smaller lakes are surrounded by very steep rims that rise high above the liquid level. This is an unusual formation, as lakes on Earth, known as karstic lakes, typically result from erosion or the dissolving of limestone, which creates shallow and smooth edges. This terrestrial process does not seem to account for the features of many of Titan's lakes. Scientists now propose that these could be explosion craters that have subsequently filled with liquid methane. According to models, Titan was once a colder world where nitrogen, not methane, fell as rain and snow. This liquid nitrogen would have seeped into the crust, forming subterranean pockets. As cryovolcanoes in Titan's past released the greenhouse gas methane into the atmosphere, the world began to warm. This warming would have caused the trapped liquid nitrogen below the surface to evaporate and expand. This built pressure within the pocket until the overlying crust violently ruptured, leaving behind an explosion crater. There is still a great deal to be learned from the Cassini data. The lakes of Titan represent just one small facet of the mission's findings, and scientists will continue to piece together these complex puzzles for many years to come, improving our understanding of the entire Saturnian system. It is a hope that future space agencies will pursue missions with the same ambition and achieve the same level of success as Cassini, as there remains an immense amount to discover out there. Enceladus, for instance, is perhaps one of the most compelling objects in the entire solar system, and yet it is merely the sixth largest moon of Saturn, and in natural light it appears quite unremarkable. However, there is far more to Enceladus than its simple appearance suggests. It is a dynamic, icy world, with plumes of water vapor erupting from its southern hemisphere. Thanks to the extraordinary Cassini mission, we have been able to study and observe Enceladus in magnificent detail. We have possibly learned more about it than some of the larger and closer moons of Jupiter. But while we have seen much of its exterior, the moon's interior still holds a great many secrets. To understand this world, we can first consider where Enceladus is situated within our solar system. Enceladus is currently recognized as Saturn's 14th closest moon. The word currently is used because Saturn possesses tiny moonlets within its rings that could potentially be reclassified as moons in the future. It holds the distinction of being the second closest major moon, surpassed only by Mimas. This position places its orbit just outside of Saturn's primary rings. Its path follows the plane of the rings with high precision, and it completes a full orbit around Saturn in only 33 hours. An interesting orbital characteristic is its 2-to-1 resonance with Dione, which is Saturn's fourth closest major moon. In simple terms, this means that Enceladus circles Saturn twice in the same amount of time it takes Dione to orbit just once. This orbital relationship is thought to be what keeps the path of Enceladus from settling into a perfect circle, subjecting the moon to continuous tidal deformation. The significance of this process is that these relentless tidal forces generate heat within the core of Enceladus. From what we can observe, the moon's surface appears to be composed almost entirely of clean water ice, with very few rocks or other contaminants present. Because of Saturn's great distance from the Sun, the outermost layer of water on Enceladus is frozen solid. This makes Enceladus, in essence, a world with a frozen ocean, a vast sphere of water ice. The purity of its surface materials makes the moon one of the most reflective bodies in our solar system, with a bond albedo of 0.81, a value nearly identical to that of fresh snow. Consequently, it is also one of Saturn's coldest satellites. Its noon temperature plunges to -200 degrees Celsius because its bright white surface reflects a large proportion of incoming sunlight back into space. Yet, at a depth of about 30 to 40 kilometers beneath the surface of Enceladus, the pressures increase. Here, the thermal energy created by the tidal flexing of its orbit raises the temperature enough for the water ice to transition into a liquid state. It is quite possible that a complete global ocean, a liquid mantle of sorts, lies beneath the ice crust, much like the magma mantle that supports Earth's rocky crust. At a minimum, scientists are confident that a massive reservoir of liquid water exists under the Moon's south pole. The most direct evidence for this comes from the enormous plumes of water that are ejected from cracks in the crust, a phenomenon known as cryovolcanism or water volcanism. These jets are remarkably active, consistently blasting approximately 250 kilograms of water into space every second, reaching speeds that exceed 2,000 kilometers per hour. This velocity is so great that most of the water vapor particles overcome the weak gravity of Enceladus. They then enter into orbit around Saturn, where they coalesce to form the planet's E-ring. This particular ring around Saturn is extremely diffuse, making it difficult to see unless it is backlit by the sun. When viewed from this angle, sunlight filtering through the fine water particles gives the ring an exceptionally blue appearance. In fact, due to its uniformity, this ring is regarded as the bluest object in the solar system, surpassing even the planet Neptune. The E-ring is Saturn's second most distant ring, and it spans a width of 2,000 kilometers. Its structure is also profoundly shaped by the orbit of Enceladus. As the Moon erupts, its plumes create delicate, tendril-like formations within the rings. These features, however, tend to smooth out as Enceladus continues along its orbital path. Throughout its mission, the Cassini spacecraft was able to fly directly through these plumes, allowing it to analyze the substances being expelled. This maneuver was not part of the original plan, as scientists were unaware of the plumes until Cassini arrived. Fortunately, Cassini was equipped with an instrument named the Cosmic Dust Analyzer, which was intended to determine the composition of tiny dust grains orbiting Saturn. This instrument proved equally effective for studying the plumes of Enceladus. Because it was not specifically designed for this task, the data it returned might not present the complete chemical picture. Still, while water was the most abundant substance it found, the analyzer also detected amino acids, carbon dioxide, nitrogen, and methane. The presence of amino acids is particularly noteworthy, as they are the fundamental building blocks of life and are known to exist around hydrothermal vents on the floors of Earth's oceans. This discovery raises profound questions about whether Enceladus might harbour its own thermal vents, and if so, whether ecosystems could have formed around them. While the evidence for a subsurface ocean is strong, scientists remain uncertain about the precise internal structure of Enceladus. It was once believed that the Moon was composed of water from its surface all the way to its centre. However, data collected by Cassini indicated that Enceladus has a greater mass than previously estimated, which implies it must contain a core made of heavier materials like iron or silicate rock. The scientific community is now leaning toward the theory that its interior is differentiated, meaning it is a celestial body with distinct, defined layers. An object of this size is not necessarily expected to be differentiated. At only about 500 kilometers across, it is just on the cusp of being in hydrostatic equilibrium, the state where its own gravity has pulled it into a rounded shape. There are other objects of a similar or smaller size, such as Neptune's moon Proteus, that are not in hydrostatic equilibrium. In any case, if we assume it does possess a differentiated interior, its core is likely made predominantly of rock. This is a crucial detail because hydrothermal vents in the Moon's water ocean would need to originate from a rocky core. A rocky ocean floor would also supply the essential nutrients and minerals that we believe are necessary for life to emerge and evolve. The existence of the plumes is clear evidence of thermal activity, and the amino acids found within them lend further support to the idea of a rocky core. As Cassini flew over Enceladus, it also created maps of the Moon's thermal emissions. This mapping revealed that the jets align perfectly with features that have become known as Enceladus's tiger stripes. These are immense depressions, each roughly 130 kilometers long, 2 kilometers wide, and 500 meters deep. It is thought that these stripes are tectonic fractures in the Moon's icy crust. What is truly remarkable about the surface features of Enceladus is the near-total absence of impact craters across its southern hemisphere, and the relative scarcity of them elsewhere. This strongly suggests that the surface of Enceladus is very young. While the Moon does have a tenuous atmosphere formed from the water ejected by its plumes, it is nowhere near dense enough to burn up asteroids before they strike the surface. A portion of the water from the plumes inevitably settles back onto the surface, which gradually smooths it over time. This ongoing resurfacing is another reason why Enceladus is so round for such a small celestial body. Indeed, aside from the tectonic fractures and a few craters, the topographical variation on Enceladus is quite minimal. There are no mountain ranges to speak of, though one could identify what might be called rough terrain around the South Pole when viewed at high resolution. In what is perhaps the highest resolution image we have of its surface, it genuinely resembles a giant glacier. It is interesting to observe that even in this limited view, there are both smooth sections of ice and more jagged regions. Over the North Pole, the most apparent difference is the greater number of craters found there. Tectonic fractures are also present in this region, yet what's noticeably absent are the plumes found at the opposite pole. This absence suggests a much older surface, one that has been exposed to impacts for far longer, resulting in a heavily cratered landscape compared to the youthful terrain around the South Pole. During its passes through the southern plumes, the Cassini spacecraft captured detailed images of the terrain surrounding the tiger stripes. The landscape revealed is truly extraordinary, bearing little resemblance to anything on our own planet. The icy surface appears to have been compressed, folded, and moved about, creating a striking collection of fractures and unique formations. The ability of Cassini to approach Enceladus so intimately was a remarkable accomplishment in its own right. It is a privilege to have such a clear perspective on a world so distant. With the conclusion of the Cassini mission, however, a quiet void has been left. We currently have no active spacecraft in the Saturnian system to continue the investigation of this moon. Over the years, numerous mission concepts have been proposed, but each was ultimately cancelled before development could begin. An ideal future explorer would be a probe capable of penetrating the ice to reach Enceladus's ocean, or one that could at least meticulously analyze its plumes for any potential biosignatures. While the Dragonfly mission is indeed planned for the neighboring moon of Titan, its objectives do not include Enceladus. A few new proposals are being considered, but even if one is selected, we are likely still at least 2 decades from its arrival. This long wait is poignant, as we can only wonder what mysteries remain concealed beneath that icy shell. And that concludes our look at the captivating moon, Enceladus. For those who wish to stay informed about discoveries like this across the cosmos, we are pleased to offer a weekly newsletter. Our designer, Peter, has crafted what we believe is a truly beautiful email experience. You can subscribe using the link provided below. It serves as an ideal way to remain connected between our video releases, offering concise and focused updates on the latest fascinating developments in space. We are committed to providing only meaningful content, without any spam or unnecessary filler. Each edition delivers the most recent news, compelling visuals, and valuable insights directly to you. If you appreciate the content in Astrum videos, we think you will find this a welcome addition. We invite you to join the newsletter and continue exploring with us.